Hello everyone. Over this and the previous week, we have looked into various methods to estimate the design seismic load. Today, we will summarize these methods and also understand when which method should be used. So, we have looked into equivalent static method, which was the simplest method. So, we have looked into equivalent static method, where the magnitude of lateral force was depending only on the estimated fundamental period of the structure, and the distribution along the building height was based on simple formulae. Since equivalent static method considers only the estimated fundamental period, it is important to understand that it can be applied only for buildings with regular distribution of mass and stiffness. Further on, we looked into dynamic analysis method, particularly two methods, which are response spectrum method and response history method. And as it is clear, these methods are based on few, if not all, modes of oscillations of the building, and therefore the magnitude of lateral force depends on different natural vibration modes, and thereby the distribution of mass and stiffness over height has been considered. However, other limitations of equivalent static methods is still present in the dynamic analysis method. Okay, so as we have seen about the equivalent static method, which is the simplest method for design seismic load calculation, and in this case we usually apply to buildings with first translational mode of oscillation having mass participation of at least 80%. We have seen the flow chart where we were first determining the total design lateral force for the building, then distributing it vertically across different floor levels, and finally distributing it among different lateral load resisting elements based on floor diaphragm action. Moving to response spectrum method, we were considering different modes of oscillations for the design seismic load calculation, and therefore it was applicable to all buildings. In this, the first step was to determine, in this method the first step is to determine dynamic properties of the building, which include natural periods and corresponding modes of oscillations. We also found out modal participation factors and modal masses corresponding to different modes. After finding the dynamic properties of building, we were able to determine the lateral force at each floor in each mode. This was based on code prescribed design spectra, which depends on natural period of the structure and soil type, that is the site classification. After finding the lateral force at each floor in each mode, we combine different modes to find the lateral force at each floor considering all the modes. After finding these, we are able to distribute the floor forces among different lateral load resisting elements based on floor diaphragm action. In the response history method, which is the most elaborate method of all these three methods, and therefore it is suitable for irregular buildings as well as critical and special buildings in higher seismic zones as well. In this method, what do we do is that in this method we start with application of certain seismic load in form of ground motion records. Now, the code suggests that if our building is located in zone 2, 3 or 4, we will be using 30 far fault motions, and if our building is to be located in zone 5 or zone 6, we will be using 60 ground motion records, 30 from far fault and 30 from near fault motions. And these records are available in Annexure E of IS 1893 Part 1 2025. They are already scaled for seismic zone factor, that is Z, but they are not scaled for the elastic force reaction factor. So, depending on the structural system which you choose, such as OMRF or SMRF or CR wall or eccentrically braced frame, based on that you already know the value of elastic force reaction factor R, you need to multiply these ground motion records by 1 by r. Alright, now you have the records ready with you for which you want to analyze your building systems. At this point, it is important that we have an analytical model ready with us on which we will apply the time history analysis to obtain the response. The response will include maximum base shear as well as the stress resultant and deformation demands on various members. One thing is very clear from all these methods that we need an analytical model of the building structure. Now, let us understand that this analytical model is necessary for all critical and special buildings as well as irregular, important and normal buildings. So, we have classified buildings into different categories based on their functionality into normal, important, special and critical buildings. In case of normal and important buildings, for regular buildings, that is the buildings which do not have a structural irregularities, you can skip the analytical model, you can continue with your equivalent static method. However, if your building has irregularity, then you need to prepare an analytical model. When you are developing an analytical model, it must cover certain aspects accurately. It must cover geometry of building and its components, that is various structural members like beams, columns, etc. It should cover accurately the material properties, such as for the structural element such as beams and columns, we need to know the modulus of elasticity, Poisson's ratio of concrete or steel, whatever is the case. For the soil, we need to know the shear modulus, Poisson's ratio, subgrade reaction, etc. So, it is important to conduct these tests before preparing any analytical model. If we do not have the test data available, we can still use some empirical expressions which are specified by the code. We should also imbibe the three-dimensional distribution of mass and stiffness in our analytical model. So, for example, if there is a water tank at the rooftop, you need to consider that there is a lumped mass at that point. So, that is how you need to consider the three-dimensional distribution of mass and stiffness. Now, further on, you need to consider or cover the boundary conditions at the supports and joints as closely as possible. In case of soil, you need to consider the soil flexibility by use of translational or rotational spring, and if you are using response history method, you must be using Rayleigh damping. Since this course is about design and detailing of various structures, we are not going into detail about the Rayleigh damping. For that, you can refer to appropriate textbooks or the code. Okay. Once you have the analytical model ready with you, then it is high time to apply load on the analytical model. So, what are the loads that we will be applying? We will be applying dead load, imposed load and earthquake load. Dead load, as it is clear, it is mostly from the self weight of members and the load which is always going to be present over there. So, this will be obtained from IS 875 part 1. So, it is important to use the latest version of the code. So, if IS 875 goes through revision, then it is suggested that you use the most latest version of the code. The second load which you shall be considering is your imposed load or commonly called as live load. So, this is based on IS 875 part 2. The third load, since we are doing the seismic design, we shall be doing is earthquake load. This is based on IS 193 part 1 and part 5. Part 1 deals with general provisions and part 5 deals specifically with buildings. So, here the earthquake load can be computed as we have seen over the over this and previous week that now we are equipped with 3 different methods: equivalent static, response spectrum and response history methods for determining the earthquake load. So, all these 3 methods are actually giving you the earthquake load. Now, this earthquake load is applied in a distributed manner along the building height, and we have seen it earlier. How do we distribute it along the building height? Whether it is in the equivalent static case where we distribute it using a code specified expression, in case of response spectrum or response history method, we actually consider different modes of oscillations, and therefore, we are already able to distribute these design earthquake load along the building height. Once we have the load defined on our analytical model, it is time to consider different load combinations that we need to consider in our analysis. So, this slide contains information about the basic load combinations. When you are designing reinforced concrete and steel structure using limit state method, or when you are designing masonry structures designed using working stress method, and when you are designing any soil designed by WSM, that is working stress method. So, it is important to note at this point that the code IS 1893 part 1 2025 version also suggests about designing reinforced concrete and steel structures by limit state method, but it gives an option to design masonry structures and soil by working stress method, okay, which is usually followed. So, at this point it is important to understand that in all these load combinations, what is important to understand is that these earthquake loads do not have any coefficient with them, or they do not have any load factor with it. What does it mean? Okay. So, by now, if you have tried the problem statement, if you have tried solving the example problem which we discussed using equivalent static and response spectrum method, if you have tried doing the same problem using the previous version of the code, that is the 2016 version, it is likely that you would be finding the design seismic load which will be lower than the design seismic load calculated using 2025 version of the code. Okay. You will find, if you compare, you will find that the value of seismic zone factor has increased, but at the same time now the code gives you relaxation that you do not have to apply any partial safety factor of load when it comes to earthquake load. If you see the load combinations provided in 2016 version of the code, you will find that this load combination is given as 1.2 times of dead load plus imposed load plus minus earthquake load, all in the bracket. So, every load was multiplied with 1.2, and similarly in the other cases as well. So, that is the relaxation that code has now given. So, you increase your design seismic load, but you need to check your building design for slightly relaxed load combinations. Okay. So, now if we are analyzing any building for ground shaking in one horizontal plane, in one horizontal plan direction at a time, let us say that we are interested in the seismic analysis of any given building for seismic excitation only along x direction. So, here I have also put the screenshot related to basic load combination. So, here I have also put the details of the basic load combinations which we have seen in the previous slide, and in this case when we are considering analysis along x direction, then we consider ELX instead of EL, and if we are analyzing our building for seismic response along y direction, then this EL will be replaced by ELY, and so on for every load combination that is a change what we have done in this case. Now at this point the code also suggests that in some cases you might like to analyze your structure for ground shaking in two orthogonal plan directions together, that is along x as well as along y. So in that case you need not consider the total design seismic load along x as well as the total design seismic load along y. So in that case we have different load combinations. So one of the load combinations, if you see, if you are considering the earthquake load along x as 100%, you are taking only 30% of the earthquake load along y, or vice versa, that is 0.3 ELX plus minus ELY. Alright, this is true for all the load combinations listed over here. So by now you would be familiar with how these load combinations are being derived from the same basic load combinations that we have seen earlier in this slide. Okay. Now if you are having a very critical building, let's say nuclear power reactor, in that case you may have to analyze your building for ground shaking in three orthogonal directions, that is two orthogonal plan directions x and y and one vertical direction, that is z. So let us see the load combination for them for this case. So in this case we need to consider 100% of earthquake load along one of the directions and 30% of the earthquake load in the other two directions. So it is ELX plus minus 0.3 ELY plus minus 0.3 ELZ, and as you can see here we have put it for 100% for ELY and 30% for ELX and ELZ. Here we have put 30% for ELX and ELY and 100% of ELZ. One of them will be for 100%, the other two will be accounted as 30%. Okay, if you look further into the code also gives you detail about if you are analyzing any building for ground shaking in one horizontal plan direction and one vertical direction, which means you are analyzing, let's say, for ground shaking in x as well as ground shaking in z. Then in that case the load combination is also given in the code, but that is seldomly applied in real time and in real life analysis and design, and therefore I have not covered that in this very class. So once you have defined these load combinations, then in that case if you are using your equivalent static method, you will analyze the analytical model for different load combination and you will determine the stress resultant and deformations in the members considering different load combinations, and you will take the envelope maximum values for designing those members. In case you are using dynamic analysis method, that is either response spectrum or response history method, then in that case we will first perform linear static analysis considering dead load and imposed load only, and then we will determine the stress resultant and deformations in members considering the earthquake load, and then we will combine all these loads as per the stipulated load combination that we have seen and determine the stress resultants and deformations in members considering load combination. So what is the difference? If you are using equivalent static method, you need to apply all the load combinations at one go, but if you are using dynamic analysis method, you need to check the building for only dead load and imposed load, then you need to check the building for only earthquake load, and then you need to check it for dead load, imposed load plus earthquake load. Okay, once you have the stress resultants and deformations in different members which will be required for design, we will be using relevant codes such as IS 456, IS 800, IS 13920, IS 18168, etc. for design and ductile detailing of various building structures. For example, if you are designing any reinforced concrete building for seismic resistance. If the reinforced concrete building is comprising of only ordinary moment resisting frame OMRF, then you shall be using only IS 456. But if the building comprises of SMRF, a special moment resisting frame, then you need to use IS 456 as well as IS 13920, and so on for other structural systems as well. So now the question is, which method to use for what kind of structures? So as it is evident to us, equivalent static method is the most simplified and most rudimentary method. So that will be used only when you have certainty of good seismic performance. How will you get certainty of good seismic performance? The structural system should be good, the building should not be irregular. Okay. So therefore, in zones 2 and 3, if your structural system comprises of at least MWB, that is masonry with band, special moment resisting frame with infill for RC as well as steel, and special concentrically braced frame with infill for in case of steel structure, so then only you can apply your equivalent static method. So if your building is having ordinary moment resisting frame or ordinary concentrically braced frame, and your building is located in zone 2 or 3, then in that case you cannot use equivalent static method, you are bound to use any of the dynamic analysis methods. Okay. For regions with higher seismicity, that is zones 4, 5 and 6, the criteria is even more stringent, that is you cannot even use equivalent static method for masonry buildings with bands. You need to have both bands and reinforcement in case of masonry buildings. Then you cannot use equivalent static method for analyzing buildings which have only a special moment resisting frame without shear wall. You cannot use that. Okay. Therefore, in those cases you need to switch to dynamic analysis, either response spectrum method or response history method. So these two methods apply to all structural systems in all zones. Further, if your building is critical or special building, let us say it is a critical care hospital building, or if it is a nuclear power reactor, then in such cases it is recommended that you use response history method, which is the most elaborate method. It can also be used for important and normal buildings, but for critical and special buildings it is recommended that you are using response history method. Further on, for irregular buildings it is recommended that you use dynamic analysis methods. Okay. And if your building has natural period more than 0.4 seconds, then in that case it is always recommended that you use one of the dynamic analysis methods. Okay. In any case you can apply equivalent static method considering irregularity of building or the functionality of the building. However, for complicated cases it is best recommended that you adopt one of the dynamic analysis methods. However, for buildings with inferior structural systems, you cannot use the equivalent static method. So all these details are also available in table 9 of IS 1893 part 5 2025. You may have a look into the code for further information. In the next class we will look about buildings which have some torsional irregularity and how to account for torsional irregularity in buildings. Thank you.